The ethane process furnace at a petrochemical plant experienced premature failure of its radiant tubes. These tubes developed longitudinal cracks, some of which extended through the entire thickness of the tube. They were made from HP+W heat-resistant steel casting. Analytical techniques including scanning electron microscopy and energy-dispersive X-ray spectroscopy were utilized to examine the microstructure and chemical composition of the tubes. Microhardness testing and structural analysis via X-ray diffractometer were conducted to assess mechanical strength and structural integrity. The findings revealed that the failure mode of the tubes was a result of both high-temperature carburization attack and creep damage, leading to intergranular cracking. The overheating, likely occurring during decoking operations, was identified as the root cause of the failure. It was recommended to improve control over furnace temperature to prevent overheating. However, if the furnace temperature exceeds 900 degrees Celsius during operation, replacing the alloy must be considered. In such instances, a steel casting material with higher resistance to carburization and creep damage, such as the HP+W grade, was proposed as an alternative. Industries like oil and gas, fertilizers, thermal power, and petrochemicals necessitate alloys capable of withstanding high temperatures. These specialized alloys, referred to as heat-resistant alloys, HRA, demonstrate exceptional mechanical and thermal properties under high temperature conditions. From the failure case described, several lessons can be learned to prevent similar incidents in the future. Material selection. Careful consideration should be given to the choice of materials, especially for components subjected to high temperatures and corrosive environments. In this case, the HP+W heat-resistant steel casting was not sufficiently resistant to carburization and creep damage, leading to premature failure. Regular inspection and testing. Implementing regular inspection and testing protocols using various analytical techniques such as scanning electron microscopy, energy-dispersive X-ray spectroscopy, micro-hardness testing, and structural analysis via X-ray diffractometer can help identify early signs of degradation or failure. Temperature control. Improving control over furnace temperature is crucial to prevent overheating, which can accelerate material degradation and lead to catastrophic failures. Implementing better temperature monitoring and regulation systems can help mitigate this risk. Consideration of alternative materials. If operating conditions exceed the limitations of the current alloy, consideration should be given to alternative materials with higher resistance to carburization and creep damage, such as the HP+W grade steel casting mentioned. It's important to evaluate the suitability of alternative materials through rigorous testing and analysis. Industry standards and best practices. Adhering to industry standards and best practices for material selection, operation, and maintenance of equipment in high-temperature environments is essential to ensure reliability and safety. By incorporating these lessons into their practices, industries like oil and gas, fertilizers, thermal power, and petrochemicals can minimize the risk of premature equipment failures and ensure the longevity and efficiency of their operations. Thank you very much for watching the video. You may consider to subscribe, like or sharing the video, if it is worth doing. Bukhara Tashkent Bishkek Almaty, BTBA, gas pipeline is an operating gas pipeline running from Uzbekistan to Kazakhstan,
passing through Kyrgyzstan. The pipeline runs from Bukhara, Uzbekistan through Tashkent, Shymkent, Taraz and Bishkek to Almaty, Kazakhstan. The Bukhara-Tashkent-Bishkek-Almaty pipeline is the main source of gas supply for Kyrgyzstan and southern part of Kazakhstan. The diameter of the pipeline is 1020 mm 40 in, and the annual capacity of the pipeline is almost 22 billion cubic meter (BCM) of natural gas. Construction of the pipeline started in 1967. In 1968, the pipeline reached to Tashkent, in 1970 to Bishkek, then Frunze, and in 1971 to Almaty. The pipeline connects to the Central Asia-China gas pipeline near Akurtob, Kazakhstan, where the Akurtob boosting compressor station was built in 2016.
Explore our YouTube channel, Petrosult, for captivating videos covering science, engineering, technology, and energy topics. The primary aim of launching this YouTube channel is to facilitate the exchange and dissemination of knowledge and experiences among professionals and amateur